Hi, welcome back to the only YouTube channel that's not listening to Fleetwood Mac's advice on this one. I had a problem a couple of weeks ago. This is a 1993 Bentley Continental R, and this doesn't fit, and this needs to fit. This is a Bosch iBooster, and, well, most of one. It suffered a terrible fate when it met a hammer because the motor stopped working because I took it apart and I broke it. So before we dive in and talk about what I did, let's talk about what is an iBooster and where did we start. Superfast Matt has a pretty good explanation of when he disassembled one on his channel. Essentially, there's a BLDC motor that drives some gears, that drives a helix that pushes the master cylinder in and out, and in the middle of all of that, there's a little Hall effect sensor with a magnet that moves back and forth a little bit, so there's no need for an external brake position sensor or brake pedal sensor. I wanted to know what was behind this surprisingly hard to get into motor. It's PCB mount, you got this Deutsch plug on the end of it. That's not a Deutsch, but whatever. And frankly, I know basically nothing of what this does. I need to figure that out. Okay, there we go. All right, much happier with that. It's very clear this was never designed to be taken off, frankly. Oh, I couldn't have done that any better. Woo. All right, I'll take it. For those of you following along at home, if our goal is electronically assisted brakes because we don't want to deal with the lines of a power booster, we have a big cam so we don't want to deal with the vacuum issues on a vacuum assisted unit, this works perfectly fine for most applications. But I have notes. Basically, the only way to run it is in a fail-safe mode where the CAN bus has no idea what it's doing, so it just defaults to a set value. There has been some efforts in trying to decode what the hell is going on with CAN bus, but it's mostly proprietary manufacturer nonsense, and none of it's very fun at all. The biggest criticism of all, and the one that I'm most upset about, is that it doesn't look good. It's a big, weird gray lump, and I want to change that. So, with that all being said, I spent the last 3 weeks building this. Now, this is very much a revision 1 because I've already changed half a dozen things in here, but the general principle uses a lot of the same components that the iBooster did, but all we're doing is moving the motor from beside the unit to in line with the unit. I think it's important to remember that this channel is the spiritual equivalent to the one penguin that wandered off into the Antarctic abyss in that one Werner Herzog film. Now, this creates a very tricky thing in that we're running the pushrod through the center of the motor. It's actually a larger diameter than the factory booster used, so it's plenty strong, but it's still very, very tricky as far as tolerance goes. I made some parts. This is the point in the video where I will use rotor and stator interchangeably. They are not, and they mean two completely different things. But anyways, obviously we didn't want a ton of steel lying around, and we needed a way to actually hold this in the middle. So I made these, which fit entirely based on, wow, it's stuck to the table, into the actual guide that they give you on the plastic little thing. And then I got one for the other side as well. I put little drive lugs on it so that it should handle the torsional load fairly well. I did 4 holes in the mill, brought it over to the lathe, and then test fit the actual, that looks great on camera, piece on the end of the stator holder. I'm going to part this off. I'm going to do the other side, make sure it fits on the bearings, and go from there. Jesus, Mary, Magdalene, you are. And in a very Wes Anderson way, let's take an overhead shot and go over what we built. So these are the parts, and before we open this can of horses, let's remove all of the pieces of hardware that are McMaster Car or off-the-shelf, just generic industrial components that you can buy at your local hardware store or McMaster Car. A lot of these parts have a machined inner edge for a bearing, but the actual alignment is either from a machined outer edge, like on this part, or dowel pins, like on this part, which makes that a little bit easier. Let's also add in the circuit board that I designed specifically for this project and then forgot. We have 2 things to do to this board. First of all, we need to put on our Amphenol plug, and then on the back side, we have to add our wonderful little crimp connectors. One there, and one that I positioned directly in the middle of the board. Yeah, nothing wrong with that. So importantly, this is one of the 13-pin Amphenol plugs board lock that has the 2 heavy pins and a bunch of light pins, and then that just makes that a lot easier for the theoretical slightly higher amperage that we have going on here. Real quick, shout out to JLCPCB for sponsoring this video. I actually had boards from them on the way when they reached out to me and asked if I was interested in being sponsored by them. I've always found JLCPCB to be easy, affordable, and reliable for these projects, so they sent over these boards. It's truly effortless to upload your Gerber file to get an instant quote and order in minutes. It's as easy as online shopping. And for 1 to 8 layer PCBs, they start at just $2, which makes it a no-brainer for these prototypes. JLCPCB's lead time is also incredible, with PCB production in just 24 hours, and these boards, I think they were 4 days from when I placed the order to when they arrived on my doorstep. It's truly fantastic. Discover easy, affordable, and reliable PCB manufacturing with JLCPCB. Follow the link in the description below to get $70 off your first order. Let's talk about what's left. This is the factory master cylinder that came on the iBooster. It's from a Honda Civic, and I'll put the specs up now, but that's actually a pretty well-performing master cylinder. This also is set up with the bolt spacing to take a standard off-the-shelf tandem master cylinder. So it can use both this factory one or the aftermarket one. This sits in the drive ring and is threaded for the helix, and this helix is cut off the factory plate with a cutoff wheel. Out of what we have left is this mid plate and this end plate, which I'll show in the CAD file, but these are going to be made out of stainless steel and actually chromoly steel in the case of this. So at the moment, they are just plastic for the sake of test fitting. And not counting one metal McMaster car gear, and not counting the factory gear that I brought over earlier. This is a glass-filled nylon gear. I intend to manufacture all 3 of these out of a glass-filled nylon material as well that's not FDM printed. I also tried to match the gear size and everything to the Bosch unit and not go any smaller or weaker than they did. I'd actually love to know what your thoughts are in the comments on a laser sintered gear versus a injection molded gear with a resin printed mold, or a few different options like that. These two rods travel the full length of the booster from the actual mounting flange to the master cylinder itself. I wanted to use the exact same original design as the brake booster did, in that it has a full line of contact from the very front of the unit to the actual master cylinder itself, to rely on that for all of the strength laterally. While we're here, let's put in some bearings. That's feeling pretty good, and then I think we're doing a pretty good job of being against the seat on the back side. Really quick, I was going through my sockets looking for a pressing tool, which is exactly how that works. And let me get this on camera. My 24 millimeter is like, you see that? That's really weird. Because there's like, huh. Alright, so these press in a lot easier than they hammer in, so I'm going to keep doing that. Just to double check. Nice. Alright, so we're going to start putting some of this together. First of all, this little intermediate shaft should, theoretically, yeah, slide through there. It doesn't go that far. Somewhere in there will get us pretty close. And again, a lot of these gears and stuff are temporary. Actually, this one very much is, because this originally had like a weird thrust washer setup, which no longer exists. But, and then this and this go together very nicely. And that spins. And then on this side, the recessed, or the actual washered side of these slide right on and keep it on both sides. This and this slide right in there and should stay pretty happy. I'm going to try and adjust this. Oh, I forgot the dowel pins. Alright, for this side, this and this go there, and then there's a stud for that rear bearing that has to sit there, and then that seems to play really, really nicely. This has a little bit more play in it than I'd like axially, but I can put a shim in there. All it's doing is causing that to rattle a little bit. Anyways, that part of it is done. This main gear, I'm using the exact same design that the original unit had, in that it has a plate, which again, this will be made out of steel, not plastic. And then it just has a press fit collar that sits on the outside, kind of like a sandwich here. And then this and this gets pressed together, and then that's how it handles the interface with this plate. This is the stator from this motor. Nothing about this part is straying from it being a standard BLDC 3-phase or 3-phase DC, however you want to call it, motor. It operates at 12 volts, and I'll put up the spec sheet. I believe it's a 400 watt motor, so it's actually a fairly powerful little critter at 2800 RPM or so, I believe. Assembly on this is going to be interesting. Obviously, this slides in there very nicely, and oh, I forgot to mention that on the back side of this, everything's falling. On the back side of this, and everything's sticking to my table, this slides in there and is part of the motor. That is working pretty well. A little bit of a moment of truth, because I have not test fit this yet. So, and that does not go. Wow, that was kind of underwhelming. Anyways, this fits very snugly in here, which is ideal. You know, it's not a press fit, but it is, you know, I can push it in, and it sits on a lip in the bottom of this slot. I theoretically can push this in. So far, I'm being proven wrong. I'm thinking I should have done that before I assembled everything else, because I do not know if that's seated completely or not. Okay, now moment of truth. It's kind of hard to tell now. This is going to grab this and pull this in very dramatically. This side also has a bearing and a coupler. The bearing on this is designed to basically be shimmed out to adjust the runout of all of this. Hopefully, we can just assemble this and assemble this. Okay, so far so good. What's going on? Oh, this, I don't know if you can tell, needs to be indexed correctly to these, because it has to fit within this. This to these, because it has to fit within this. I didn't do that before pressing in the motor, so like right now we're like there, which means we're off index. So gotta fix that. Okay, update. I kind of accidentally gave knockouts there and there to help press the motor out, so good for accidental design, I guess. Then this goes on the outside and aligns there. Okay. One thing that an engineering degree probably would have done well is the idea that things don't fit perfect in the real world. You know, like this spacer is a great example. If I would have designed this a few years ago, I would have made it basically an interference fit, and then it would have been nonsense and probably not worked as well. So I guess, like, in the growth of everybody's personal industrial design language, mine is basic engineering concepts. Yeah, I don't really like this either, but the thing is that I have the, obviously, plug receptacle for this, but I don't really need any of the plug yet outside of just power. So these are my 25 amp 10 gauge wires, and we're going to save the plug wiring for just a moment. I'm also going to take a big risk, and this is the controller for the board, which is a Teensy 4.0. Because of room, I have to solder it directly to the board. I do not know if I was able to design a board effectively, and I guess we're finding out. I guess there is a bit of a risk here because the only program on this Teensy is a Blink program, but, you know, we'll give it a shot. Hey, look at that. Certainly not the cleanest setup I put together in my entire life, but overall, we have something going here. So, we have jumpers running from our board. This actually does mount to the motor, but I made a mistake in that the mounting flange for the board is on this external shell, which is fine, except I have no idea what place I need to solder that on to the motor housing. So, anyways, that's called revision 2. This is sort of hooked up here. So these are to my leads. I have my oscilloscope hooked up over there. And then I have, what else do I have? The board's hooked up. The Teensy's in there. It's hooked up to my laptop. And I have an open loop program running here on this. We should talk about this board. I designed this board in-house, which, you know, that comes with its own set of problems, and I already have notes. But essentially, it's really based on Simple FOC's power driver board, the one that they kind of phased out of development a little bit. But they're very nice to put all of that open source stuff up there. So I am essentially using their schematic. I mounted a Teensy 4.0 on the board itself, so we don't have to deal with that at all. There's like the network of capacitors and resistors to make everything like each other and not blow up for some reason, which I don't totally understand, but that's the reason I'm not an electrical engineer. And then my obsession with board lock Amphenol connectors knows no bounds. And yeah, they've gotten a lot of my money recently, and I don't know how to feel about that, but they sure do look nice, and that's what counts. One of the notes from earlier that I had was that the Hall effect sensor that actually controlled the pedal motion had an outside run to this motor controller, and you had to tie it in separately. This is all internal. A quick note on that, I'm probably going to change that second Hall effect for motor position back to this board. I have the room to do it. The problem is that because I'm not centered, I don't have a center position. It's kind of hard to read, but that's why it's revision 1. T2, which is 2 radians per second. T4. It is actually spinning very nicely. I can build a motor. All right, so all of this stuff whose name isn't Teensy is very toasty. Very, very toasty. Don't know why that's getting hot. That shouldn't get hot, I don't think. I'm not sure on this one. This is a linear regulator which steps the 12 volt from these down to the 5 volt to power the Teensy. The quick math is that it has 1 watt, 1.4 watts, I believe, that it dissipates at, I believe these packages are like 40 degrees Celsius per watt. So I'm like, this draws 200 milliamps, so it should be fine, but, I'm on the upper limit of a linear regulator, and I might look into that. One of the things about open loop control is that it's just wildly inefficient. Like it doesn't know what's going on, so it's just kind of throwing whatever at the wall and sees what sticks. Once we get encoding into there, it should manage power a bit better, but these, could probably benefit from some heat sink. Luckily, I have a ton of aluminum surrounding it in basically every single aspect. So part of the problem is that I don't know what I'm doing, but part of the problem also is that this is a very, very low phase resistance motor, i.e., when you take a multimeter and you go across pins, it's very, very, very low. Lower than either one of my multimeters can measure. So from all of the research that I've done, it seems like low phase resistance motors need a lot of very precise control to run them at the amperage that I'm trying to run them. Now, I'd love to show you the Hall effect sensor and how it functions as a load cell and how it kind of ties all of this together. However, I bought really small connectors, and I bought connector ends that I could just make my own cables because I really didn't want to pay for the whole, cable assembly, and I didn't want to cut them down, yada, yada, yada. And, yeah, they're way too small for me to deal with, and we're just gonna buy actual cables. So that's a good lead into how I think I'm going to control all of this and how I think I'm going to make it work. We already have a load sensor with the Hall effect. That's essentially functioning of how hard is the pedal pressing against how far the pedal is moving at any given moment. The board knows where the motor is because it has a Hall effect sensor mounted to the end of a shaft, so it can figure out motor position. And all that's left is essentially a control algorithm for how hard you press the pedal relates to how much the motor helps out as you're pushing the pedal down. So this board was originally designed to sit on the back of the existing booster before I changed anything mechanically, and I just wanted to handle the communication protocol and this nonsense. So goal number 1 was to create a serviceable product, because this is not serviceable, this theoretically is. The other part of it is that I wanted to override some of the CAN bus communication protocol, so we put 2 kinds of CAN bus communication into this. We put a couple of analog and digital line in for various sensors, so more on that in just a minute. And then also we put in just a standard analog in to where a potentiometer could be, in theory, used to control the amount of brake assist that exists within this device. I like my piece of engineering here. I think it's very pretty, but it is a very specific use case for applications where you just don't have a lot of room in that direction. I think the board and controlling it on this side is a much more practical use from this video. Anyways, that'll probably do it for this video. If you liked the video, please like, subscribe, comment down below, and thank you guys very much for watching.